Hello and welcome back. We're now ready to take a look at systems with infinitely many solutions. In this first example, we see that we have two lines in two dimensions, and if we look carefully at this, we can't distinguish the two lines from one another. Well, that's because they're sitting right on top. They're exactly the same line. In fact, the second equation is simply double that of the first equation. So if we produce our Gaussian elimination problem and construct our augmented matrix, 1, negative 2, 4, 2, negative 4, and 8. And it looks like the equations are in a good order. I see that I have a pivot of 1 up here already, so I'm not going to do any swapping of the two rows. But I do want to cancel out this 2 down here, so I think what I'm going to do is take negative twice row 1, add it to row 2, record the results in row 2. So if I take negative 2 times the first row, I'm going to get the matrix. We're leaving the first row the same. 1, negative 2, 4. And negative 2 times 1 plus 2 is 0. Negative 2 times negative 2 is positive 4, minus 4 is 0. And this is one of those cases where, depending on what happens next, there could be 0 or infinitely many solutions. However, negative 2 times 4 plus 8 is in fact 0 again. So we get one of those situations where the second equation really does not give us any new information. So we could write out our solution as follows. We could say x minus 2y equals 4, and the second equation just says 0x plus 0y equals 0. And that's not a very useful equation. That's just confirming what we've already known for a long time, that 0 equals 0. So in this case, it appears that there are infinitely many points along here where the two lines intersect. So I have to construct some way of building an ordered pair that says, well, as long as x equals blank and y equals blank, this is going to be a solution to the system. So I'm going to think about the relationship here. It just must be the case that the difference between x and 2y has to produce 4. You can think of probably lots of different ways to do that. So if x is 8, that'll be 8 minus 2y equals 4. So that means y would have to equal 2 so that 8 minus 4 equals 4. So the ordered pair x, y equals 8 and 2 is a solution, is one solution. And that would be the point somewhere, well, it's not on the graph, but x equals 8, y equals 2. That's not a very good way to write this solution. In particular because it doesn't tell me that there are infinitely many solutions. It just says that 8, 2 is one of them. So as long as I pick the value of one of the variables, it really doesn't matter which one, although usually in the row in which we have our leading 1, so there's our leading 1, we only have a leading 1 in the first row, that's going to be the variable that I'm going to express as a function of any of the other variables. So I can write from the statement that x is equal to 4 plus 2 times y. Now the second equation did not give me any information about what y could or could not be. Therefore I'm free to pick its value, and I'm going to say that y is free to vary. In mathematics we often call this a free variable because it is a variable and it's free to vary. So I have to think of a value that would work here, but there are infinitely many of them. So, as in the previous video, as long as we pick a value for y, we say let y be some fixed value. Let's call that, it could be c, or it could be s, or it could be any other letter that's not it's not in use already. So I'm going to choose y equals c. So remember, c is just some arbitrary number. It could be any number, and that's what we mean by arbitrary, is it could be any. So as long as y is equal to c, that means that I can compute x, right? X is going to be the result of taking 4 plus twice whatever that value of y is, which in this case is c. So I have my solution. I have that as long as y equals c and x is equal to 4 plus 2c, I have a solution. And I'm going to write it in vector form, but it can be written as an ordered pair as well. I have the solution x, y is equal to, well, x is equal to c, y is equal to 4 plus 2c for any value of c. Now I could just check this if I let y be equal to, excuse me, I have these two values backwards here. I misplaced my x and my y. My y is going to be fixed to some number, and then my x is going to be 4 plus 2 times that number. So if for instance, in our example up here, when y was equal to 2, then x would be 4 plus 2 times 2, which is 8. And so 8, 2 is in fact a valid solution as we have listed. But it's not the only one. There are infinitely many choices. In fact, we could see here that here's a point on that graph, and that corresponds to an x value of 4. Well, and it looks like that's the point 4, comma 0. So let's check our solution. If y is equal to 0, x is going to equal 4 plus 2 times 0, which is 4, and again, that's a valid solution. It also appears that when y is negative 2 and x is 0, that's also a valid solution. So if I choose negative 2 for C down here, 4 plus 2 times negative 2 is 0, and again, I've produced a valid solution to that system. So choosing the free variable, the way we're always going to do this is we're going to produce the Gaussian elimination, and then any row in which you have a leading 1. So by leading 1, we just mean the first non-zero value. Remember, these diagonals are always going to, we're going to try to reduce them to become 1s. That variable, any variable that has a 1 in its row, is going to be considered a variable that is not free, but more on that later. Here's a 3 by 3 case. 3 equations, 3 variables, and that means we're in 3 dimensions. Now we can see here that these 3 planes intersect along this continuum right here. And that's going to be a full line of different points. So we're going to want to make sure our solution displays that. And our matrix for this problem is going to be 1, negative 1, 1, 1, 1, 0, 1, 2, 2, negative 1, 2, 3. So there's our starting matrix. And I'm going to begin operating on this. It looks like I'm happy with my first row. I could interchange rows 1 and 2 if I would rather have a 0 already in place right there. And you know what? I think I am going to do that because I know that ultimately in this position I'm going to need a 1. So I am going to just go ahead and start off by interchanging rows 1 and row 2. So that's going to provide me with 1, 0, 1, 2, 1, negative 1, 1, 1, and 2, negative 1, 2, 3. So now I'm going to cancel out the second row, and the way I'm going to do that is I'm going to take negative 1, row 1, added to row 2, put the results in row 2. So we're going to take negative 1 times this whole first row, and we're going to add it to row 2. Row 1, row 3 are unchanged. We're only changing row 2 right now. Let's see what happens here. So here we're going to get negative 1 times 1 plus 1 is 0. Here we're going to get negative 1. Here we're going to get 0. Here we're going to get negative 1. Negative 1 times 2 plus 1. So it looks like we're doing good so far. We need to eliminate this 2 down here. So to do that, I'm going to again pivot off my first row. Negative 2 times row 1 added to row 3. We're going to make the change in row 3. So I'll put my coefficient here, negative 2 times all of these guys added to the bottom row, which will produce the matrix first 2 rows unchanged. And now the third row will become 0. Negative 2 times 0 minus 1 is negative 1. Negative 2 times 1 plus 2 is 0. Negative 2 times 2 plus 3 is negative 1. All right, so far so good. I don't see any rows in which all the coefficients have been eliminated, leaving only the non-zero constants. So far so good. But I do see something interesting here. Rows 2 and 3 look hauntingly similar. In fact, they're identical. And this is where we're going to actually eliminate all of the values, make 0 out an entire row. And so at this point, at this stage in the game, my objective would be, now that I have the 1, 0, 0 here, I'm going to want to turn this into a positive 1. So I can go ahead and do that next. I'm going to take negative 1 times row 2, store the new result in row 2. So I'll have 1, 0, 1, 2, 0, positive 1, 0, positive 1, 0, negative 1, 0, negative 1. So far, so good. I have the 1, 0, 0, 0, 1. I'm going to now work on canceling out this negative 1 here. So that means I'm going to have to just go ahead and take row 2 and add it to row 3, store the results in row 3. That's going to produce 1, 0, 1, 2, 0, 1, 0, 1. And now 0, 1 plus negative 1 is 0, 0 plus 0 is 0, 1 plus negative 1 is 0. So we get this elimination of that third row in this example. We cannot go any further, in fact, because our next step would be to turn this bottom component into a 1, but unfortunately there's nothing I can scale 0 by in order to make it a 1. Therefore, this is where the elimination process has to end. And as such, notice that this guy up here will also have to stay a 1. So that's going to indicate that the first equation is not only going to depend on, it's not just going to be x equals, it's going to be x plus z equals. And x plus z equals 2 is officially the correct statement. So we are done at this point. There's nothing we can do. Interchanging the first and the third row won't do anything because that'll just put this 1 down at the bottom here, and I don't want that 1 there. All right, so we can begin reading off what the equations say. The first one says x plus z equals 2. The second equation says 0x plus 1y plus 0z, or y, equals 1. So I've been able to identify the value of y exactly. So basically that continuum that we saw up here, this is a position where all the y values are equal to 1. I don't know how well you can see this, but right there where y equals 1, that line goes all the way up and down for y equals 1. That's pretty cool. All right, so that means, and the third row, of course, in this case is not going to give me any additional information, so forget that. Now I see that y has to be equal to 1. So that means that if I were to write out my solution set, if I were to write it as a vector, you could again write it as an ordered triple, x, y, z equals, all I know for a fact is that y has to equal 2. But there's no information about what z has to equal. There's only information about what x has to equal if you know z. So it tells me that x has to equal 2 minus the value of z. But again, no information on z, therefore z is going to be our free variable. It can be anything we want it to, provided that that the sum of x and z is equal to 2. And there's lots of ways to do that. All right, so that means I'm going to let z equal some arbitrary constant. Again, you can use any letter provided it's not one of the letters that you're using as a variable. And now if z is equal to c, and that's, by the way, that's going to be the value of z. It's just going to be any number that we want. And that means that now, in translation, x is going to equal 2 minus that value that z is going to take on, which is c. And that gives me my solution for x as well. So in my final statement, I'm going to say, well, z is going to be any arbitrary constant. X has to be 2 minus that arbitrary constant. It is directly related to the value of that constant. And c can be any number that we want it to be. So as just kind of a quick check, as just a little check, we can say, well, if c equals 0, because that's an easy choice, that means x, comma y, comma z, or one intersection point of these three planes is going to be the point. Well, y is equal to 2, c is equal to 0, therefore x is equal to 2 minus 0, or 2. So what I should be able to verify is that 2, 2, 0 satisfies these. So 2 minus 2, wait a minute. And this is a good check because I'm seeing that 2 minus 2 plus 0 is not equal to 1. So let's see if we can detect our mistake. This is a good learning experience here. If you don't check your work, it's hard to know whether your final answer is right. So we said here y is equal to 1. Okay, there we go. There's our problem. So we said y is equal to 2 here, but y is in fact equal to 1. So that means that y has to be equal to 1. And let's check our work now. So 2, 1, 0, is that in fact a point? 2 minus 1 is 1, plus 0 is 1. 2 plus 0 is 2, good. 2 times 2 is 4, minus 1 is 3, plus 2 times 0 is still 3, so 3 equals 3. Looks like a valid point. Well, another thing you could do is you could just plug in these 3 symbolic values for x, y, and z in this equation and just make sure that they balance out. So that's it. That's how we work with systems of equations with infinitely many solutions.